Welcome to this course on probability and statistics. This is an introductory course, or you can say a first course on the probability and statistics, and it is quite useful for all branches of science and engineering. So to begin with, we introduce algebra of sets. This is required because the modern theory of probability is based on the set theory. So here we introduce certain elementary concepts of sets which will be directly used in our definition and concepts of probability. So to begin with, we start the discussion on what is set, classes and collections. So we have start with a universal set, let us call it omega, and then we also have the usual notation for the empty set as phi. We call a set of sets to be the class and a set of classes to be a collection. As an example, consider suppose omega is the real line R, and we consider the collection of intervals starting from A to B, where B is greater than A, for every real number A. Then this CA is a class of sets for each A, and then if we collect all these classes CA into a set called script E, then this is a collection. For any two sets A and B which are subsets of omega, let us consider the relation A related to B if A is a subset of B. Then the relation R is reflexive and transitive. It is symmetric when omega is equal to phi. We introduce some further conventions and notations. If the index set I is empty, we make the convention that union of EI's is empty, and also intersection of EI's is the full set omega. The second of this convention looks to be rather surprising. However, it is motivated by the fact that if we take more and more sets in an intersection, then it becomes smaller. For example, if I have two index sets I1 and I2 such that I1 is a subset of I2, then intersection of EI where I belongs to I1 contains intersection of EI where I belongs to I2, primarily because the more sets means the intersection becomes smaller. Hence, the smallest possible index set, that is phi, should lead to the largest intersection, that is omega. This convention is also consistent with De Morgan's laws. For example, if I write union of EI, I belongs to I, complement is equal to intersection EI, complement I belonging to I. Let us take I to be phi, then the left hand side is equal to phi, complement is equal to x. This indicates that we should take intersection of EI when I is an empty index set, then this should be equal to the full space omega. Let us introduce the concept of indicator function or characteristic function. The characteristic function of a set E is defined to be 1 if x belongs to E, and it is 0 if x does not belong to E. Alternatively, we can write the set E as the set of all those points for which x chi Ex is equal to 1. Clearly, indicator function of the empty set is always 0, and the indicator function of the whole space is always 1. There are certain exercises here. For example, if a set A is a subset of B, then the indicator function of A is always less than or equal to the indicator function of B. Conversely, if the indicator function of the set A is always less than or equal to the indicator function of B, then A is a subset of B. A simple proof of this is that if we consider chi A x, then it is equal to 1 for all x belonging to A. And since A is a subset of B, this implies that chi B x is also 1 for these points. Now, for the points where chi A x is equal to 0, include certain points where chi B x may be 1, and for other points chi B x will also be 0. Therefore, chi A x is always less than or equal to chi B x. We have certain elementary properties of the characteristic functions. For example, characteristic function of an intersection is equal to the product of the characteristic functions of the two sets. It is also equal to the minimum of the indicator function values for those two sets. The proof can be simply obtained by definition. For example, chi of E intersection F x is equal to 1 if x belongs to both E and F and 0 otherwise. That means it is going to be equal to 1 only if chi E x and chi F x both are 1, and in every other case it is going to be 0. So that means it is equal to the product. In a similar way, the minimum of chi E x and chi F x is going to be 1 only if both chi E and chi F x are 1. That means chi E intersection F x is equal to 1. Similarly, the indicator function relations for the unions, complementations and differences are also there. For example, chi of E union F x is equal to chi E x plus chi F x minus chi of E intersection F x. It is also alternatively equal to the maximum of chi E x and chi of F of x. Once again, to look at the proof of this, we can see that if we write maximum of chi E x and chi F x to be say 0, then both of chi E x and chi F x must be 0. Hence, chi of E union F x will be equal to 0. If maximum value is 1, then either 1 or both of chi E and chi F must be 1, and so chi of E union F will also be 1. The other properties of chi function, for example, chi of E complement is equal to 1 minus chi E, chi of E minus F is equal to chi of E intersection F complement x, which is chi of E into chi of F complement from the property 2, and chi of F complement from the above property is equal to 1 minus chi of x. So these are some of the useful relationships for the indicator function. We have all heard about the limit of sequence of numbers. For example, you easily understand that limit of an is equal to a if for every epsilon greater than 0 there exists capital N such that modulus of an minus a becomes less than epsilon whenever n is greater than or equal to capital N. This shows that the sequence an is closer to the number a, the values of the sequence n become closer to the number a as n becomes large. However, the similar concept is not available for the sequence of sets. Here we define it in a slightly different fashion. So, in order to introduce the concept, we introduce the concept of lim sup of En and lim inf of En, are called limit superior of En or limit inferior of the sequence En. So, consider a sequence of subsets of omega called En, we define E upper star is equal to lim sup of En, which is equal to the set of all those points which belong to infinitely many values of n. What does it mean? It means that from the whole space we take up those points which belong to En for infinitely many values of n. The collection of such elements will be called limit superior of En. In a similar way, we define limit inferior of En called E lower star. It is the collection of those elements of omega which belong to all except maybe a finite number of values of n. That means they belong to almost all the values of En except maybe for a few of them. If E upper star and E lower star are the same sets, then the common value is called the limit of En, and we say that the limit of the sequence of sets exists. By the definition, it is clear that in general we will have E lower star as a subset of E upper star, primarily because if X belongs to E lower star, then already we are committing that it is belonging to infinitely many values of n, because it is belonging to all except a finite number. That means definitely it is belonging to infinitely many values of n. Therefore, in general, E lower star is always a subset of E upper star. When it is equal, we say that the limit exists. Let us consider some simple examples of application of the concept of the limit of sequence of sets. Consider, for example, En set defined to be an open interval 0 to 1 minus 1 by n for n is equal to 1, 2 and so on. Here if we calculate the limit inferior, then if you consider any point in the interval 0 to 1, then since 1 by n goes to 0 as n tends to infinity, for every number a between 0 to 1, we can find for every 0 less than 1, we can find capital N such that a is less than 1 minus 1 by n for all n greater than or equal to n. This shows that a will belong to the interval, a will belong to E lower star. This also shows that a will belong to E upper star. So E lower star is equal to E upper star is equal to the interval 0 to 1. So this is a case where the limit exists. Let us take another example, the sequence of closed intervals from 1 by n to 1 minus 1 by n for n is equal to 2, 3 and so on. Once again, if we utilize the argument as given in the example 1, if we consider any element a between 0 to 1, then after a certain stage it will belong to the set En for all n greater than or equal to some capital N. Therefore, once again the E lower star, that is the limit infimum of this sequence, will be the interval 0 to 1, and naturally E upper star will also be 0 to 1 because it is a superset of E star in general and it cannot be go beyond the interval 0 to 1. Notice that here the point 0 itself and the point 1 itself do not belong to E lower star or E upper star, because for no value of n these points belong to the set. Now I will give one example where the set En is defined in has a finite number of points, and here E lower star and E upper star are different. Consider the set En given by 0, 1 by n, 2 by n, n minus 1 by n to 1 for n is equal to 1, 2 and so on. Then if this particular sequence can be explained like that, if we consider E1, then it is the set 0 to 1. If we consider E2, then it is the set 0, 1 by 2, 1. If we consider the set E3, then it is equal to 0, 1 by 3, 2 by 3, 1. Clearly, the points 0 and 1 belong to all the sets. Therefore, E lower star, that is the limit infimum, must contain the points 0, 1. Now we say that no other element of the form, say P by Q, can belong to all the sets ENs even after a certain stage. For example, the point half, it will belong to once again E4 because 2 by 4 will come, it will belong to E6 because 3 by 6 will come. So it will belong to infinitely many sets, but it will not belong to all but finitely many. Similarly, if I consider say 1 by 3, then it will be there in E3, it will be there in E6 as 2 by 6, it will be there in E9 as 3 by 9, etc. So it will once again belong to infinitely many sets, but it will not belong to all but finitely many. Suppose we consider a point say 2 by 3, then it is belonging to E3, then it will again belong to E6 as 4 by 6, it will again belong to say 9 as 6 by 9, etc. Therefore, we conclude that all the rational numbers in the interval 0 to 1, all the rational numbers of the form P by Q in the interval 0 to 1 will belong to infinitely many of the ENs. Therefore, E upper star will be the set of all those rationals in the interval 0 to 1, whereas the limit inferior is equal to the interval and the set consisting of the points 0 and 1. Another example is we consider the sequence as split into two parts, that for even ordered sets En is one particular set say A and it is equal to B for n odd. Then E lower star is the set of points which are common to both A and B, because if we consider a point which belongs to both of them, then for all but finitely many sets of En, X will belong to them. However, if a point is not in one of A and B, then for infinitely many values of n it will not belong. Therefore, the only points which can belong to E lower star are which are common to both A and B. On the other hand, any point which is belonging to either A or B will be there in infinitely many sets, and therefore the E upper star will be A union B. Naturally, you can see that E lower star is equal to E upper star if and only if A is equal to B. Let us consider a disjoint sequence of sets. If we apply the definition of limit superior and limit inferior, then we note that there are no elements of omega which belong to two sets, because the sets are disjoint. Therefore, no point in the set omega can satisfy the property of belonging to either infinitely many ENs or all but finitely many points of En. Therefore, limit inferior as well as the limit superior both are the empty set, and it is equal to limit of the sequence of the sets. In order to derive the limit inferior and limit superior using mathematical arguments, one may look for the alternative representations for these sets. For example, limit inferior can be written as union intersection En n is equal to m to infinity and m is equal to 1 to infinity. In a similar way, limit superior can be written as intersection union of En n is equal to m to infinity, m is equal to 1 to infinity. To prove these statements, let us take the first case. Consider a point x belonging to limit inferior of En. By definition of the limit inferior, it implies that x belongs to En for all but finitely many values of n. This implies that from a given m onwards, x will belong to all the sets En. That means x will belong to the intersection of En, n is equal to m to infinity, for some m is equal to 1, 2, etc. Clearly, this implies that x belongs to union intersection En, n is equal to m to infinity and m is equal to 1 to infinity. On the other hand, if we take x belonging to union m is equal to 1 to infinity, intersection n is equal to m to infinity En, then this statement implies that x belongs to intersection of En for some m is equal to 1, 2, etc. Now this statement once again implies that x belongs to En for all but finitely many values of n, which was actually the definition of limit inferior. Therefore, we have both way implication for all the statements, and this proves that limit inferior of En is equal to union intersection En, n is equal to m to infinity, m is equal to 1 to infinity. If we apply the same argument for the limit superior, then we get that if x belongs to intersection union En, n is equal to m to infinity, m is equal to 1 to infinity. So I am taking the right hand side first. Now this implies that x belongs to union En, n is equal to m to infinity for every m is equal to 1, 2, etc. Now if we say that x belongs to the union starting from every m, howsoever m large may be, this definitely implies that x belongs to infinitely many values of n, because if it was belonging to a finitely many values only, then after a certain stage x will not belong to the union of En's. However, it is belonging for every value of m. This means that x belongs to En for infinitely many values of n. which is actually the definition of limit superior. Now to look at the argument in the reverse way, if x belongs to the limit superior, then this implies that x belongs to En for an infinitely many values of n. Now once again, if x belongs to infinitely many values of n, then no matter for which value of m you start with, x will belong to certain sets after that, and therefore this statement implies this. Now since this is true for every m, this statement implies that x belongs to intersection union of Ens. This proves the statement 2.